Welcome. In this tutorial, I'll show you how to catch performance regressions before they ever reach a pull request, using K6 and Signadot Plans. A plan is a small, reusable validation workflow that a coding agent authors from natural language and runs against a live environment in your Kubernetes cluster. Plans are built on actions, typed building blocks your platform team governs. The workflow runs through two skills. Signadot Plan has your agent draft a plan, confirm it works, then tag and commit it as a versioned artifact. Signadot Validate then reads a diff, picks the right plan, spins up a sandbox with the change wired in, and runs it. Today we'll use that flow to guard a latency-sensitive path, author a K6 plan from a single sentence, capture a baseline, introduce a realistic change that passes every local check, and watch the plan catch a 6-second latency cliff inside the cluster. Let's get started. Some performance regressions slip past every check you run. The build passes, the unit tests pass, the diff reads clean, and the real cost only shows up when production traffic hits the change under load. The app on screen is HotROD, a ride-sharing demo running in Kubernetes. On every dispatch request, its front end calls the location service twice, so the dispatch path is latency sensitive and worth guarding. The cluster is already connected through Signadot. We start with the load test plan. A Signadot plan is a reusable load test that runs inside the cluster. I describe it in plain language, and the agent writes it. 10 virtual users for 30 seconds, posting a dispatch to the front-end service with 2 gates. The first caps P95 latency at 1,500 milliseconds. The second caps the HTTP failure rate at 1%. A breach makes K6 exit non-zero, which fails the plan. The agent writes the script, wires it into the plan, and tags it hotrod-dispatch-load. Once saved, the plan guards against any future changes to this path. First, the baseline. I run the plan against the unchanged code. Both gates pass. 10 virtual users drive 496 requests in 30 seconds with P95 latency at 680 milliseconds, well under the budget, and a 0% failure rate. That is the healthy shape of the dispatch path and the reference we measure every change against. Now, a realistic change. A developer picks up a ticket. Rate limit location resolution to prevent a spike from overwhelming the location service. They reach for a sync.Mutex, lock the function body, and defer the unlock. The reasoning sounds right, and the code is wrong. A mutex does not rate limit calls. In this placement, it serializes them. Resolve locations calls location twice per request, and one lock covers both calls, so every request holds it for the full round trip. Under load, 10 concurrent requests stop running in parallel and queue behind one lock. Build, vet, and unit tests all pass because the test runs one call at a time and never contends. Nothing on the laptop flags it. To test latency honestly, the change has to run on the real path, inside the cluster, with nothing extra in front of it. I hand the change to the validate skill. It builds my front end into an image and forks the in-cluster front end deployment to run that image, isolated on its own routing key. The fork sits next to the real location service, so the only latency we measure is the code under test and its real dependencies. A tunnel to my laptop could add network time and distort the threshold, so we keep the test in the cluster. Now I point that same load at the changed code, using the fork's routing key. The plan still targets the front end by its normal in-cluster address. The routing key is what sends the keyed request to the fork, the one copy running the mutex. The run fails. K6 exits 99 and the latency gate fails. P95 jumps from 680 milliseconds to 6.37 seconds. The failure rate holds at 0. Every request still succeeds, it just waits. Throughput collapses from 16 requests a second to under 2, and the virtual users drain as they queue behind one lock. The plan caught a change that passed every local check and quietly broke the live dispatch path. The plan did its job, so I revert the mutex. The lock is gone, the import is gone, and the local checks stay clean. A real fix would reach for a token bucket limiter or a bounded semaphore, neither of which serializes every request. Then I run the plan one more time against the reverted code. The plan passes again. P95 back at 682 milliseconds. Failure rate still 0. The regression never left the development loop. It never became a pull request, and no reviewer had to catch it by eye. Lastly, I tear down the sandbox and disconnect. That is the full loop. One reusable plan authored from a sentence, a realistic regression that passed every local check, and a 6-second latency cliff caught inside the cluster on the real path before it ever reached a pull request. The next change to this path reruns the same plan with nothing new to write.